All right, the last little thing we're going to look at here, I think, with the inverse functions is some notation. And I want to see where it comes from. Suppose we have domain A, range B, and function f maps x, or function f maps domain A set A to range set B. Now, if x is in the domain, then it corresponds to a value in the range. One way to represent that is f of x. Typically we call it by a different letter, y or something, but it is certainly valid to say if x is the domain value, its range value may be written as f of x. But if this is its inverse function, if this is a function and if this is its inverse, then this is the domain value and this is the range value. And what we may say then is this is the input that proceeds to this output. But if this is a value, if I simply have a value in this set, then there's a way to represent this expression over here. Just like if I take thing in circle, and this is f of thing in circle, now if this is thing in box, I can say this value is f inverse of the thing in the box. It is f inverse of f of x. Now slow that down a little bit. If this is x, we may write that as f of x. If this is thing, then we may write this as f inverse of thing. But that collection of symbols and that little symbol are equal to each other. They're the same value. And that gets us to this notion. If you take f inverse of f of x, the value you get is x. It is as if these have canceled out. In fact, that's where the notion of canceling out arises. When you apply inverse functions in sequence, f is a function, f inverse is its inverse. If you apply inverse functions in sequence, then the result is the argument. So if let's suppose 4 is in set A, then we know if you take f of 4, you're going to get something. And then if you take f inverse of that, you get back where you started from. You get back to 4. So if we assume these are inverse functions, then f inverse of f of any value you care to put in here, 16. If we assume this is a valid definition, then that's equal to 16, because when you apply inverse functions in sequence, it is as if they cancel and you're left with just the argument. Now, it's true starting from the left and going to the right and then returning to the left. This would also be true if we just did the whole thing backwards. It is okay not to just take f inverse of f, but we may also reverse this. If I take f of f inverse of something, again, you've applied inverse functions in sequence. It is as if they cancel, and you're left with just the value itself. When you apply inverse functions in sequence, which sequence is irrelevant? When you apply inverse functions in sequence, the result is the argument. And so, assuming everything is defined, the expression f of f inverse of, and you may put anything on God's green earth you want in here if we assume they're defined. If this is 20, when you apply inverse functions in sequence, it is as if they cancel, and you're left with just the argument, 20. And so the two expressions we're going to take from this are the following, that f of f inverse of x is equal to x, and f inverse of f of x is equal to x. And that's also true not only if you have a single value, but that's true if you have a larger expression. And so we may write f of f inverse of any expression you would care to put in here. I used to teach with a fellow named Mr. Collins, and he used to always use the word blob. F of f inverse of blob. Assuming everything is defined, f of f inverse of blob is blob. Whatever blob happens to be. So again, assuming everything is defined, f of f inverse of. You can put anything you care to in here. 6x plus 1, that's equal to 6x plus 1. Oops, plus 1. we can take f inverse of f of anything we want, blob. So we can have f inverse of f of blob. It is as if they cancel. You're left with just the argument blob. So whatever you put in here, if this is sine of x, f inverse of f of sine of x, assuming everything is defined, is sine of x. And so it's this property. This is the generic way of stating it. But that property, when you apply inverse functions in sequence, the result is the argument. We will use that as a tool to generate several properties later on to investigate the behavior of the exponential and the logarithmic functions. And so that's another one of the basic properties.